If you've ever taken an economic geology course, you probably learned about porphyry, orogenic gold, IOCG, and VMS deposits, which are important reserves of iron, gold, copper, zinc, and lead. But what about rare earth elements? Rare earth elements are a group of 15 lanthanide elements plus yttrium and scandium with an increasing demand in society. With unique physical, chemical, magnetic, and luminescent properties, rare earth elements are vital ingredients in many industrial and high-technology applications, especially in clean and alternative energy systems such as wind turbines, rechargeable batteries, and electric vehicles.
There are multiple types of rare earth element deposits, including placer and sediment-hosted deposits, carbonatite-hosted deposits, and A-type granite-hosted deposits. Today, we will be focusing on A-type granite-hosted rare earth element deposits, of which only a few have been discovered worldwide, including in Canada, Mongolia, Alaska, and China. One such deposit is the highly enriched Strange Lake Plateau, located on the remote northern border between Quebec and Labrador, which is one of the best-studied A-type granite rare earth element deposits in the world. Due to the increasing demand for the rare earth elements, understanding how they are concentrated into economic deposits is important for future exploration and development of rare earth element resources.
Based on the isotopic data discovered at the Strange Lake Pluton, these deposits are thought to originate in a continental rift setting. As the crust spreads apart and the magma upwells, decompression melting forms the starting parental magma for the rare earth element A-type granitic deposit. Although the exact mantle composition necessary for these deposits is debated, continental rifts provide the high pressures from the thick continental crust and the anhydrous magma composition necessary for minimal partial melting. Low partial melting is necessary to form nephelinitic magmas, which are required for A-type granite formation. Nephelinitic magmas are silica undersaturated with an aluminosilicate composition.
After the nephelinitic magma is first produced in a continental rift setting, a series of fractional crystallization stages results in the enrichment of the high field strength elements. High field strength elements form valences greater than 2+, which in geochemistry typically includes the rare earth elements, plus titanium, zirconium, niobium, molybdenum, hafnium, tantalum, and tungsten. Initially, forsterite and diopside crystallize out, followed by plagioclase feldspar. This decreases the magnesium oxide and calcium oxide in the magma, while significantly enriching the alkali concentration. Sodium and potassium are network modifiers, meaning they prevent the formation of long silica lattices and inhibit polymerization. This maintains a high solubility for the high field strength elements in the melt.
As previously mentioned, the original magma was produced from mantle rock and nephelinitic in composition, which is silica undersaturated, but the final A-type granites are granitic, so they must become silica saturated. As the magma reads through the crust, assimilation of around 10% continental crust induces the required silica saturation, which forms the granitic melt.
The minerals that have crystallized so far are forsterite, diopside, and plagioclase, which are not hydrous and do not contain chlorine or fluorine in their structures, so these elements also enrich in the melt during fractional crystallization. If an event such as a sudden pressure change from rapid ascent of the magma causes albite-rich plagioclase to crystallize instead of anorthite-rich plagioclase, the remaining calcium and enriched fluorine can cause an immiscible silicate fluorosilicate melt to form. The zirconium, niobium, and heavy rare earth elements partition into the silicate phase, and the fluorosilicate phase will scavenge and enrich the light rare earth elements and yttrium.
Although not all A-type granite rare earth element deposits reach fluorosilicate immiscibility, it is an important enrichment mechanism for some deposits. Eventually, potassium feldspar will begin crystallizing, which increases the sodium to potassium ratio and increases water concentration further, triggering arfvedsonite crystallization. Arfvedsonite is a hydrous mineral, so it removes water and prevents the formation of an aqueous phase, which ensures the high field strength elements continue enriching within the melt. At some point during the crystallization, the enriched residual melts are emplaced at the surface and crystallize as pegmatites with concentrated high field strength element minerals. Multiple intrusions can occur at separate times, giving variation between different A-type granitic Pluton rare earth element deposits.
After the emplacement of magma at shallow depths, the pressure and temperature drop cause aqueous phase separation of the remaining water from the magma. This results in the transition from a magma-dominated system to a fluid-dominated system. The previous arfvedsonite crystallization consumes oxygen in the form of carbon dioxide, so the initial fluid is reduced with a high pH and evaluated chlorine and fluorine concentration. During cooling, a series of reactions with the surrounding minerals oxidize the fluid and decrease its pH. The acidic halogen-rich fluids attack and decompose early formed high-field strength elements bearing minerals like bastnasite, alpidite, fluoride, and perchlor. This process remobilizes these elements through the formation of chloride, fluoride, and hydroxyfluoride complex. After remobilization, further decrease in temperature destabilizes the complex and causes the high-field strength elements bearing minerals to reprecipitate, forming the final rare earth element A-type granitic deposit.
Although rare earth element enriched A-type granitic plutons evolve through the processes discussed above, variation between deposits exists depending on the exact evolution pathway and whether fluorosilicate-silicate immiscibility occurs. There is also some uncertainty on the exact formation mechanisms of these deposit styles. Currently, the Bocan Mountain A-type granitic pluton in southeastern Alaska has undergone significant exploration for rare earth elements and is nearing the construction stage for development, and the highly enriched Strange Lake Pluton in northern Quebec is anticipated to move towards future production. As demand for rare earth elements continues to increase, understanding the exact deposit model will be critical to discovering and producing more enriched A-type granitic deposits.